Hi, this is Mrs. La Barbara. Today I'm going to talk about SI units. So today's objective is to learn what are basic SI units and what are derived units. And by the end of the lesson, you should be able to use dimensional analysis to determine the unit of an unknown quantity. So first, what is a unit? A unit is a standard quantity with which other similar quantities can be compared. Simply put, for example, if you want to compare your height with the height of your cousin who lives in another country, you need to measure both heights with the same standard unit. So otherwise, it will be hard for you to compare. All measurements must be made with respect to some standard quantity. So there is SI unit or standard international system of units. Another name for it is metric units. So in physics, that's the unit we use. The SI system provides standard unit for scientific measurements. All quantities measured by physicists can be expressed in terms of the 7 fundamental units. So there are 7, as you can see, listed on this table. The top 4 are the ones we're going to use. I want to point out is the unit for mass, which is kilograms, not grams. So everything else does not have a prefix except for the mass. This is the standard kilograms. So besides the fundamental units, we have derived units. So what is a derived unit? So derived unit can be derived from a combination of 2 or more fundamental units. They are used to simplify notations. So an example of derived unit is Hertz, which is the unit for frequency. Hertz is derived by using 1 divided by the unit of time, which is second. So 1 over second, that is Hertz. Another example of derived unit is a Newton. A Newton is a unit to represent force. How do we get Newton? Newton is by combination of fundamental units. Mass, the unit for mass, kilograms, multiply by the unit of length, which is meters, divided by unit of time, which is second, divided by 2 times, becomes second squared. Another example is a joule. Joule is a unit for energy. How do we get joule? We combine the fundamental units by multiplying or dividing only. So in this case, we multiply the unit for mass, which is kilograms, by the unit for length, which is meters, and times meters again become meter squared. Then divide the whole thing by the unit of time, which is second squared, and so forth. Now, both unit and quantities are denoted by symbols. So how do we know which one is which symbol represent quantity, which symbol represent unit? Here are the rules. Symbols for quantities are denoted as italic fonts. Symbols for unit is denoted as non-italic fonts. For example, M can represent mass and M can also represent meters. How do we know which M is mass, or if M is a mass or if M is meters? Let's take a look. First example, 50 M equals 30 kilograms. In this case, M is italic. Since it's italic, it represents the quantity mass. So this expression means 50 multiplied by the mass, M, should be equals to 30 kilograms. The second expression, D equals to 15 M. Now in this case, M is not italic, so it represents unit. It means it's meters. In this case, this expression indicates D equals to 50 meters. Now, when we add or subtract the quantities with units, we can only add or subtract if they have the same units. Otherwise, we can't. the expression is invalid. For example, 5 kilograms plus 2 kilograms equals to 7 kilograms. That is a valid expression. 5 kilograms plus 2 meters, on the other hand, is an invalid expression. You cannot add these two quantities together because they represent different types of quantities. So another thing is, when analyzing units can help us solve problems. So when you solve a problem, the unit on the left, kilograms and kilograms on the left, should be the same as the unit on the right. We can determine a unit using equations. What does that mean? Is if you are given an equation, we can determine the unit of P. So that's units. Sometimes units like meters, kilograms, or time, seconds can be treated as algebraic quantities. That means they can be treated as numbers. So those units, sometimes we call those dimensions. Units can multiply or divide to form a new unit, or they can simply cancel out. Here is an example. What is the unit for P, which represents momentum? So given this equation, P equals m times v, where m is mass in kilograms and v is velocity in meters per second. So how do we derive the unit for momentum? So you simply write down the equation P equals mv, then you substitute m. The unit for m is kilograms. The unit for v is meters per second. So you multiply the two units together. Since you can treat the units as numbers, so you simply just combine them. So kilograms times meters divided by second. That is the unit for momentum. Let's take a look at another example. What is a unit for acceleration? We use a to indicate that quantity. Given this equation, a equals to the difference between final velocity and the initial velocity, the whole difference divided by time. So how do we do this? It's similarly, you write down the equation, then you substitute the units. Since this is meter per second minus another meter per second, so the whole thing, you still have meters per second. Divide by second again, so you divide by second 2 times, becomes meters per second squared. So again, it is very important when you do this derived units, the unit on the left has to be the same as on the right. Let's do an example. If m represents mass in kilograms, v represents speed in meters per second, and r represents radius in meters, show that a force F in the equation F equals mv squared over r can be expressed in the unit of kilograms times meters per second squared. So again, we are writing the equation mv squared and simply substituting the units for m, the units for v, and the units for r. F equals mv squared over r, so the unit for m is kilograms, the unit for v, meters per second. Whole thing has to be squared, divided by mass. After you simplify, this is what you should get. Kilograms times meters per second squared. And that's how you show this equation can be expressed using this unit. Another example. Which unit is equivalent to a Newton per kilogram? Per kilogram means divide by kilogram. A Newton is this. Kilogram times meters divided by second squared. Using this, divide by kilogram, kilogram and kilogram cancel, you should have meters per second squared. Another example. What is the unit for v squared over d? Given the unit for v is meters per second and unit for d is in meters. So again, you substitute units for the quantity. V is meter per second, whole thing squared divided by meter. So whole thing squared means top squared divided by bottom squared. When you divide, you multiply its reciprocal, 1 over m. So here is m squared and m cancels. So you should have meters over second squared. Last example. So what is the unit for stored potential energy in a spring given this equation? So in the back of your reference table, there are many equations just like this. So you should be able to determine the unit for each quantity when you are given an equation. So in this equation, PE represents stored potential energy in a spring. K is the spring constant given you. The unit is kilograms divided by second squared. And X in this equation is the elongation in the spring, which is in meters. To find out the unit for PS, again, we write down the equation, then we substitute the units. So let's see, what do we do with this 1/2? We don't do anything because 1/2 is a number, has no unit. So basically we ignore that 1/2, it has no unit. Then we write down the unit for K, which is kilograms over second squared times meter squared. So when you simplify, this is what you get. Kilograms times meter squared divided by second squared. So I hope that's helpful, and see you next time.